So what in the heck is a photoelectron spectroscopy graph? Kind of a big word. They look scary, kind of like this. What do they really tell us? First, we need to know something about ionization energy. Ionization energy is really just the amount of energy required to remove an electron from an atom altogether. The farther an electron is away from the nucleus, the less energy is required to knock an electron off the atom altogether. However, more energy is required to knock an electron off of an atom that's closer to the nucleus due to the greater Coulombic attractions. Now, back to the graphs. On this side of the spectroscope, we have a photon source. It shoots out these high energy waves like ultraviolet or X-rays. On this side, we measure the kinetic energy of the electrons. When you take the energy of the photon hitting the atom and subtract the kinetic energy of the electron leaving the atom, what you're left with is the energy that must have been absorbed, which we call ionization energy. I'm now going to turn things over to my non-cartoon friend, Mr. Dimitrowicz, and he's going to explain how what I've said applies to real-life graphs. Enjoy!
Now, I'm not sure who exactly the voice was of that cartoon you just saw, but whoever it was must be amazingly talented. Now, what I'm going to do is transition to how do we actually interpret a electron spectroscopy graph. But I'm going to refer you back to a diagram that you saw in the previous cartoon video, and I want to specifically talk to you about how the process actually works again. So here we have a very high energy photon source, and typically that's either an X-ray or sometimes ultraviolet, but we know what the actual strength of the wave is because, see this little formula right here, h nu? You've probably seen it before because that is what a quantum is. And just to remind you, a photon is just a light quantum or an energy quantum. So we know this Planck's constant is, well, a constant, and we know what frequency we're using, so we always know the amount of energy that we are hitting down into whatever sample of atoms we have. Now, we have a little receiver up here, and we call it an energy analyzer. It's very crafty, and what it does, it measures the amount of energy of the electrons when they're getting kicked off. Now, however much energy is getting put in, a bunch of it's going to get absorbed into the electrons that are down in here, and that amount of energy is the ionization energy, the energy required to kick an electron off. The remaining energy shoots up here and is kinetic energy, and that's what this machine measures. Probably a better way to look at it would be this. If I have an atom, there's a nucleus, and I'm going to draw a couple of Niels Bohr-like orbits, and I have an electron right here. So my photon comes in from the outside here and smashes into it, and that gives this electron a bunch of energy, and it's absorbed in. That's called the ionization energy. It gets shot off, and because it's getting shot off at a particular velocity, it has kinetic energy. If you take the kinetic energy and the ionization energy, it has to equal what this photon's energy was to begin with. And that's kind of the premise behind which all graphs work. So I'm going to keep the diagram of the apparatus in the upper corner over there because we're going to refer to it a little bit. But this is a reminder of what we just talked about. The photoelectron spectrophotometers on the left, they use ultraviolet, high energy ultraviolet or X-rays to eject electrons from an atom. The photoelectron spectrophotometer inputs only one type of radiation with a specific energy, so we always know what that photon's energy is. Because electrons within an atom are in different energy levels, different electrons can require, well, as you might have guessed it, different amounts of energy to eject. Electrons that are close to the nucleus are harder to remove, more attraction between the nucleus and the electrons. Valence electrons, or outer shell electrons, are the hardest to remove. The other thing you should be aware of is that a photoelectron spectrometer, it removes electrons from more than just one atom. So it's not like we run out of electrons when we're doing this process. I love this diagram. So essentially, and we can make little arrows, but the input energy is the amount of energy that the photon is providing. So this right here, if we want to draw an arrow, that goes to right here. So we have our atom represented by the letter A, and we have a certain amount of energy that's coming in to hit into it. That we call that the photon's energy. What you should be aware of is that whatever energy hits into this, a bunch of it's going to get absorbed in here, and that's called the ionization energy. I'm going to abbreviate it IE for short. And then whatever gets kicked off is going to produce energy, which is the kinetic energy. Now, you should be aware that the kinetic energy has a formula. Kinetic energy is equal to 1/2 mv squared, and I will underline the velocity here because what ends up happening is this. When the energy from the photon smashes into the atom, a bunch of it's going to get absorbed due to ionization energy, but any leftover energy is going to determine how fast the electrons are moving, because the kinetic energy at the end, if you add up the kinetic energy and the ionization energy, they're going to equal your photon's energy. And if you notice here, the faster my kinetic energy, the faster my velocity. So if only a small amount of energy is needed to remove an electron, a lot of energy is left over. So that would essentially say this: if we have an electron that's really far out, so this is the nucleus and we have layers here. If electron's way out here, right, and I don't have to use very much energy to knock off the electron, it's going to leave really, really fast. If I have an electron that's down below and I have a lower energy orbit or orbital, the amount of energy I'm going to have to use to knock the electron off is going to be very high, and it's going to leave a lot slower, a lot less kinetic energy, which is essentially everything that's written on the left-hand side of the slide. Now, one of the things that troubles students often is that whenever we're dealing with graphs, they use different labels for different parts of the graph, and that can confuse us. So I'm going to put all the different possible ways they can write on each axis, and they all mean the same thing. So let's jot these down together. So all of these, signal intensity, number of electrons, relative number of electrons, they are the same thing. And essentially, when we see them in a graph, don't get confused, they all mean the same thing. Now, on the x-axis, there are 3 different ways they can write them as well. And that would be ionization energy, binding energy, or the change in U with a subscript E. Now, the other thing you need to be aware of is the units. Since we're dealing with energy, energy typically has the unit of a joule, but a joule is really, really not very big. So we use instead megajoules per mole. Remember that mole from its previous work in Avogadro's world. And then the electron volt is another way of measuring it, and that's more in the electrochemistry world. The other thing that's really, really important to realize is that the majority of the time you're going to see that the x-axis is numbered backwards. It starts with a higher number over here and it goes to a lower number. That is not always the case. I may even show you when we start doing some of these graphs an example of that, because it really messes students up if they see it all in this direction and then all of a sudden it gets flipped. But hopefully you'll feel comfortable by the time we get working on these. The other thing is sometimes there's really large number gaps, and so they'll do little breaks in the line that look like this, these little double lines that indicate that this is not drawn to scale. So the distance, if you look from here from 1,000 to 100, is not the same as, is not equal to 1,000 from here to here, if that makes any sense. So it's kind of important when you take a look at a graph to determine what's on the y-axis and what's on the x-axis. And as you go up the y-axis, the height of the things that are on the graph are going to determine how many electrons are relatively at a particular energy level. And as you go across the bottom of the x-axis, it's going to essentially tell you how much energy was required to remove that particular electron. If you're closest to the y-axis, it requires lots of energy to remove the electron. They're the hardest to remove. If you move farther this direction, less energy to remove electrons, and they're easier to remove. Now, the next video, we're going to explore how these graphs actually look and how to interpret them. Hope this has been helpful.